In this video, we finally are able to solve our tangent line problem. So through the beginning of the semester here, we were originally introduced to a problem where we wanted to find the slope of a curve at some point on that curve. And we decided that we kind of needed some tools to be able to do that. So that's why we went and we started discussing and exploring this idea of a limit and this idea of approaching. But now we have enough information and enough resources to actually solve that problem. So what we're looking for here is to find the slope of the tangent line, or in fact the equation of the tangent line to a curve. Okay, and really what that results in is finding the slope to a curve at any point. Okay, but the way we do this is specifically to look at some point P. We're going to fix that point on our curve, and then we're going to try to find the slope at it using what we know about slopes so far, slope between 2 points. So here's my function, f of x, and I'm going to look for the slope at this point P, and I'm going to say the x-coordinate is c and the y-coordinate is f of c. Okay, so I want the slope at that point. This is what I'm looking for here, m. And to do that, I'm gonna find some other point, q, that's also on my curve. That guy's going to have coordinates x and f of x. Okay, it's a little bit confusing when I describe the curve as f of x, but also the point being at f of x. That's just saying that this point, I intend for it to move. I intend for it to be able to slide along the curve for different x values. Okay, and what we do is we find the slope then between those 2 points. And we do that by finding the change in y divided by the change in x, right? I'm going to call this NPQ, and it's going to be the change in y, or y2 minus y1, divided by x2 minus x1. Okay, well, what is y2 minus y1? Typically, we would take the larger point vertically to be like our x2, y2, or it's our kind of bigger point. So what we would do here is write the change in y as f of x minus f of c, right? Larger value minus smaller value, so that we're dealing with positive values. And that goes in the numerator then, change in y. Divided by x minus c is our change in x, okay? This guy here is going to be the slope between those 2 points. And if I color that slope in, if I make that a little bit more bold, we see that that's not a very good approximation for what m actually is. So we want to make this approximation better, and one of the ways we do that is by moving q closer to p. Okay? So again, here's my new picture. Same idea, but this time I'm going to choose q so that it's closer to p. I'm going to slide it towards p. We see the slope between these two as being a better approximation as the slope at P, right? So the slope between P and Q now is better than it was before. It's closer to the slope at P. So I'm just going to write that here. My slope formula is still going to remain exactly the same here, but now my x values are just closer to C, okay? So again, that approximation, MPQ, gets better as Q approaches P. But that's a nice kind of informal way to write things as Q approaches P. What we're really looking for here is kind of as X approaches C. How do I write this, right? I write the limit as Q approaches P of MPQ. Does that really give me my slope? Kind of, right? Kind of. But again, I want this a little bit more explicit. And what we do is we take the limit as X goes to C of MPQ. Okay, and just replace what MPQ is, and I get this guy here. With that limit, I really do get the slope at P, okay? This guy is called the slope of the tangent line to my function at x equals c. That's the slope that I'm looking for, okay? And you'll notice here that the slope really just kind of go to 0 over 0. So we are going to have indeterminate forms here for pretty much any case where we're looking at the slope of the tangent line. So there's going to be something else that we have to do, right? We know some techniques to handle when we have a limit that's approaching 0 over 0, but it's going to depend on the actual function that we have. This is pretty much as most general as I can write this formula. I've got a function, and I want to know what the slope is at c, when x is c, okay? So this shows up, all over the place. Very frequently, we're looking for a slope at c. We want to write this a different way. So the reason we do this, or what I'm about to do, is because everything here is defined between 2 points, right? What we had for p and what we had for q. I want to try to do this just kind of using the point p. I don't want to have a reliance on another point. So what we do is we kind of relabel some things here. What we say is that the change in y and the change in x, we write those so that they only are in terms of c instead of x and c. So I've got a change in x and a change in y. We use delta x and delta y to represent those, and we rewrite our slope so that it incorporates this change in x and change of y. So what I want to do is I kind of want to have something to replace x for here. Again, I only want reliance on c. So I'm going to manipulate this guy, solve for x. So I have something to plug in for x. I'm going to add c to both sides. I get x is equal to c plus delta x. Okay? I'm going to do the same thing for delta y. That's f of x minus f of c. Solving for f of x, right? I can basically plug in x as c plus delta x, okay, minus f of c. So what that does is it removes the x in my equation here. And what it allows me to do is write this slope only dealing with point P. I don't have to have another point to worry about. When I plug this all in to my slope equation here, my slope of the tangent line, that limit, I'm going to get the limit as now not x approaches c, but what happens is x approaches c, delta x here is actually approaching 0. So my numerator and denominator I'm going to replace by what I've boxed in yellow there. And again, as x approaches c, my delta x is actually approaching 0. This is the slope of the tangent line at c. It's the same quantity. I get the same thing from it. These two are exactly the same. But this allows me to write it without having some other value. Okay, so I have two forms of the slope of the tangent line here. This right-hand side, inside my limit, is actually called the difference quotient. And that term is going to come up relatively frequently. I'll use it probably a few times in this video. But that quotient there is referred to as the difference quotient. So what we have here is the slope of the tangent line at c, okay? And what we want to be able to do is not necessarily have to specifically zoom into a specific value of c. We maybe want to find a formula for the slope at any point. Maybe if we do that, find a slope as a function, then we can plug in any value and find the slope at any point on a curve. That's a little bit more powerful, right? I don't have to do this for every single c that I can think of. I can just do it in general and then have a formula for it. What this is called is the tangent line with the slope m. If f is defined on an open interval containing c, and if the limit as x goes to c of f of x minus f of c over x minus c is equal to, I'm going to write this other form, we really do have the change in y over change in x here. The new form that we got from the previous page there is this delta x goes to 0 of our difference quotient. That guy is our slope m. These are all the same quantities. Okay, they're all the same quantity. The first form that we found using P and Q, this new form where we're just kind of focusing on C, focusing on point P there. If this limit exists, then the line passing through CF of C with the slope M is the tangent line to the graph of F at that point. Okay, so now we've formally written a definition for that tangent line, and it's using both of those equations that we've had so far. And again, I want to generalize this even more. I want to kind of zoom out and not necessarily have to be at some specific point C. When we do that, what we're working with, I'm jumping ahead. Before that, there is a chance that these limits don't exist, okay? It seems like, maybe all the time, that when I take this limit, I'm always able to find the slope of a tangent line. But there are situations where that doesn't actually work out. For example, if this limit is infinite, and I'll do an example of that in the next video, but if this limit is infinite in either the positive or negative direction, we say that our slope of the tangent line is infinite. We have an infinite slope at C, okay? What this refers to is what we would call a vertical tangent, okay? So I wanted to, I will explore that possibility, but I wanted to make sure that you know that can happen. Technically, that limit, again, does not exist. We can just say that kind of the slope is undefined or is an infinite slope, but what that means is that we have a vertical tangent. Okay, so we're going to explore that in just a little bit here, but again, I want to generalize this formula, and actually what we have is called the derivative of a function. This term derivative refers to the slope of the curve, the slope of the tangent line. All of these things mean the same thing. Typically, you hear the word derivative. So what we have, the derivative of a function, and this is, again, no longer fixed at x equals c. We're going to have a general formula for the derivative, the slope at any point. The derivative of f at x is the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x, and what we're going to call that is f prime of x. Okay, so we have some different notation here. That is still m, right? That's the same m we have before, but it's not specifically at c anymore, okay? This f prime of x is a function of x, okay? Of course, provided that the limit exists. If the limit doesn't exist, well, then we can't really say that the derivative exists, okay, maybe at that specific value. This gives the slope of the tangent line to my function at any x value, at x f of x. So instead of at c f of c, I've zoomed out, and I can now find the slope of the tangent line at any point. This is more powerful, right? This gives me a formula, and if I want to find multiple slopes, or if I want to find where the slope is specifically a certain value, if I want to find where the slope is 6 or where the slope is 0, I can now solve this equation instead of plugging in a bunch of c's and hoping I get a 0 or a 6 out. Okay, so this is a little bit more powerful. I want to make a point that this difference quotient here is actually what we call a rate of change. Okay, it's an average rate of change. It's the slope between 2 points. But as soon as I take that limit, what we've got is an instantaneous rate of change. It's a slope instantaneously. It's a slope at a specific instant at a specific value, okay? Those are kind of some crucial details there. It's very easy to get those kind of mixed up, and we use this terminology a little loosely. You might hear somebody refer to the derivative as the rate of change. It is a rate of change. Semantically, it's an instantaneous rate of change, okay? We say it f is differentiable when this limit exists. Okay, and again, we know from the previous slide that there's chances where that limit does not exist. Okay, so there are times where a function is differentiable and times when it's not. I'll talk about this a little bit more with some specific examples in the next video here. We've got some notation that we need to take care of. So what we have is our limit there. We use very frequently dy dx to denote a derivative, okay? That's the same as the limit as the change in x goes to 0 of the change in y divided by change in x. So that's the same limit we saw on a couple slides, a couple previous slides. It's all the same. We use dy dx to represent that. This limit of our difference quotient, right? That's what we know is our derivative. That is the same as dy dx, is the same as f prime, is also the same as y prime. We use that very frequently. And also dx of f of x is something we use very frequently. One more. a little bit less used is this capital D notation that says the derivative with respect to x of f of x, okay? As the limit is an operator, right? We take the limit of something. We also take the derivative of something, right? The derivative is a limit. So there's this notation that kind of emphasizes the fact that it's an operator. This is kind of a command, right? I'm saying take the derivative with respect to x of f of x. Derivative with respect to x of f of x, okay? And that's exactly what we have, the derivative of y with respect to x, or the derivative of f with respect to x, okay? In the next video, I'll explore some different examples, go through this limit process to find the derivative, and talk about maybe where things are differentiable and where they aren't, and how that relates to some continuity components as well, okay? Thanks for watching.